In December 1915, a dying officer in a Russian trench solved Einstein's equations. He predicted something that shouldn't exist. He sent the math to Einstein by post and died 5 months later. A century passed before the Nobel Committee admitted he was right. This is what he predicted. This is what we still don't fully understand. Karl Schwarzschild was born in Frankfurt in 1873. By 40, he ran the Astrophysical Observatory in Potsdam, the most prestigious post in German astronomy. When the war broke out in 1914, he enlisted anyway. The army sent him to calculate artillery trajectories, first in Belgium, then in France, then in Russia. From the Eastern Front, between barrages, he wrote 3 pages. The math described what happens to space and time around a point mass. Exactly. Einstein had said the problem was too hard for a closed-form answer. Schwarzschild had one. He sent it in a letter dated December 22nd. Einstein wrote back 2 weeks later, quote, "I had not expected that one could formulate the exact solution of the problem in such a simple way. Next Thursday, I shall present the work to the Academy with a few words of explanation." On January 13th, 1916, Einstein read those 3 pages aloud at the Prussian Academy of Sciences in Berlin. The author was still on the Eastern Front. He never returned to that room. Here is the strange part. Schwarzschild himself didn't believe his own equations. He wrote that the geometry inside the critical radius was, quote, physically meaningless. 3 months later, he fell ill with pemphigus vulgaris, a rare autoimmune disease, no treatment in 1916. He was invalided home in March. He died in Potsdam on May 11th, age 42. This is what his equations said, and why nobody who could read them believed it for 50 years. Every mass has a number associated with it called the Schwarzschild radius. The formula is simple, 2gm over c squared. For any given mass, it gives a distance, the distance at which the escape velocity equals the speed of light. Inside that radius, nothing, not even light, can move outward. For Earth's mass, that radius is under 9 millimeters, a peanut. For the Sun, 3 kilometers, a Stockholm suburb. For a 10 solar mass black hole, 30 kilometers, the width of Manhattan. For Sagittarius A star, the 4 million solar mass black hole at the center of our galaxy, 12 million kilometers, smaller than Mercury's orbit. And for M87 star, the giant in the elliptical galaxy, 55 million light-years away, 19 billion kilometers, 3 times Pluto's orbit. We have a photograph of M87 star. The Event Horizon Telescope took it in 2019. The image is not of the black hole itself. It is light from hot gas swirling around it, bent by the geometry of space-time into a perfect ring. You have probably seen this picture, a funnel shape with a small marble rolling toward a deeper pit at the bottom. It is the most famous image in popular physics, and it lies. There is no rolling. There is no down. Space-time is curved, but the curvature is not gravity pulling. The curvature is gravity. The geometry of the funnel is real. The marble is the lie. At 1.5 times the Schwarzschild radius, light itself can orbit. It is called the photon sphere. A beam at exactly that radius loops the black hole, once, twice, indefinitely. A beam slightly inside spirals down. A beam slightly outside escapes outward. That is what the Event Horizon Telescope actually photographed. Not the black hole itself, the light from gas orbiting it, bent by gravity into a ring. 3 named distances, the innermost stable orbit at 3 Schwarzschild radii. Closer than that, and your orbit decays inward. The photon sphere at 1.5, and the event horizon at exactly 1 Schwarzschild radius. That is the boundary nothing returns from. Here is how to picture it. Light cones. At every point in space-time, There's a set of all directions a particle of light could travel, a cone opening into the future. Far from any mass, the cone points straight up. The future is up. Space is sideways. Get closer to a black hole, and the cone tips. Closer still, it tips more. At the event horizon, the cone has tipped a full 45 degrees, and inside, the cone tips past vertical. The future no longer points up. The future points inward, towards zero. There is no staying still anymore. There is only falling. And this is where physics does something that takes a while to accept. The Schwarzschild metric is the math of how space-time curves around a mass. Two terms, one in front of time, one in front of space. Outside the event horizon, both terms have the same sign. Inside the event horizon, those signs swap. Time becomes a direction. The radial direction becomes a clock. You can draw a picture of this. It is called a Penrose diagram, the full geometry of a black hole compressed onto a single page. Light rays travel at 45 degrees. The event horizon is two diagonal lines crossing in an X. The singularity is a wavy horizontal line across the top. Watch what happens to an infalling world line. It crosses the X. It curves toward the wavy line, and it ends there. Look at where the singularity is. Horizontal, across the top of the diagram. It is not a place you move toward. It is a time you reach because time passes. Inside the horizon, the singularity leads to itself the same way time leads, for you, to tomorrow. For 50 years, most physicists thought Schwarzschild's solution was a coordinate artifact, a glitch in the math that would disappear if you described the geometry differently. Then in 1965, Roger Penrose drew one diagram and proved them wrong. He called the central object a trapped surface. Once one forms, a singularity is unavoidable. 5 years later, Stephen Hawking and Penrose published a joint theorem that generalized the result. Take general relativity. Take any energy density that doesn't run negative. Take a trapped surface. The conclusion: somewhere, geodesics terminate. There must be a singularity. No symmetry assumption required. No special case. Singularities are not a quirk. They are mathematically unavoidable. This is what it would actually do to you. Imagine yourself in a spacesuit, in free fall toward a black hole. The first thing you would notice is what the geometry does to your body, and it depends entirely on the black hole's mass. Gravity is weaker the farther you are from the mass. If your feet are closer to the black hole than your head, your feet feel more gravity than your head. The difference stretches you. Tidal force. The math says it grows as 1 over r cubed, and at the event horizon, where the radius is set by the mass, it scales as 1 over the mass squared. For a 10 solar mass black hole, you would be ripped apart at about 3,700 kilometers, well outside the event horizon. You die before you reach the horizon. You never see what's inside. The geometry doesn't get the chance to be interesting. For Sagittarius A star, 4 million solar masses, you cross the event horizon intact. The tidal force at the horizon is about an Earth gravity over your body length, comparable to standing on Earth. You have about a minute of intact existence inside before the tidal forces ramp up. For Métis 7 star, 6.5 billion solar masses, you have 28 hours. And here is what you would see. The stars behind you fall away. The light from outside compresses radially, brighter, packed into a smaller and smaller cone above your head. The forward view, the direction you're falling, is solid black. You do not feel any wall. You do not feel any threshold. The horizon, locally, is invisible. Then, abruptly, the gradient steepens. Tidal forces accelerate as 1 over r cubed. The math says the time from pain to infinity is independent of the black hole. It is 0.09 seconds. The wait before it is what changes. The dying is the same. And this is the part Schwarzschild himself didn't believe. From every starting point outside the event horizon, every trajectory, every velocity, every angle, every world line ends at the singularity. Inside the horizon, the singularity is your future, not in some directions, in all of them. On October 6, 2020, Roger Penrose received the Nobel Prize in Physics. Quote, for the discovery that black hole formation is a robust prediction of the general theory of relativity. Karl Schwarzschild died in 1916, not believing his own answer. Roger Penrose received the Nobel in 2020 for proving the answer was forced. 104 years. The math waited for everyone else to catch up. The dying officer was right. And we still don't know what's inside. General relativity stops working at distances around 10 to the minus 35 meters, the Planck scale. Past that, the math is broken. The leading candidates, firewalls, fuzzballs, the ER equals EPR conjecture, all disagree on what happens at the horizon. The answer is open. What is actually inside? The math doesn't say. It says it can't say. What number wants the same treatment next time? Dark energy, the quantum vacuum, the Big Bang's own singularity. Pick one in the comments.